Hello everyone. In this talk, I'm going to present a new replacement algorithm, LIRS2, which is an improvement of LIRS replacement algorithm. This is Song Jiang. This is joint work with my students, Chen and Xing. We are from the Department of Computer Science and Engineering in University of Texas, Arlington. One of the major computer science technologies is the construction of memory storage hierarchy with the aim of achieving the speed of the fastest level and having the capacity of the largest level. To achieve the goal, caching is a key technique which leverages access locality to identify hard blocks and keep them in the cache. A replacement algorithm plays a critical role on caching efficacy. It works by exploiting locality for predicting future access events. There has been a large number of replacement algorithms proposed over the years. Among them, LIRS stands out with a consistently high hit ratio and low cost, with its unique way of characterization access locality. LIRS has generated a substantial impact in academia and the IT industry since its release about 20 years ago. The papers on the algorithm and its variant, ClockPro, has been widely cited. It has been incorporated in some real systems, including MySQL, NetBSD, and InfiniSpan. Obviously, we would like to identify blocks of strong locality for caching and replace blocks of weak locality quickly out of the cache. Therefore, every replacement algorithm has its defined locality measure to quantify its strength. How this locality measure is defined is a key to high hit ratio. LIRS high hit ratio is attributed to its uniquely defined locality measure, the reuse distance, which I will discuss further. Let's first take a look at the theoretically optimal locality measure, which is used by the OPT algorithm. OPT selects a block whose next access will occur fastest in the future for replacement. In this example block access sequence, block A has been accessed for a number of times. Assume this is the current time, and this block A has its last access, the second to last access, and the next access. And OPT's locality measure is the time distance from the current time to its next access time, tnext. A block of the smallest tnext has the strongest locality, and a block of the largest tnext has the weakest locality and the replacement candidate. As OPT has been proved to be the optimal algorithm, tnext is optimal locality measure. However, this tnext measure is not available online. So now let's see an online locality measure. The LRU algorithm selects a block whose last access occurred fastest in the past for replacement. So its locality measure is actually recency, which is a time from its last access to the current time, tlast. So it attempts to use tlast to estimate tnext, which is not available online. There are two issues with the LRU locality measure. The first one is faithfulness. LRU's tlast measure contradicts OPT's tnext. With new block accesses, the current time moves forward and the tlast becomes larger and the tnext becomes smaller, so the estimation is wrong. The second issue is on steadiness. LRU's tlast measure keeps changing with new accesses, causing misleading locality characterization and confusing replacement algorithm. Let's use an example to see the performance impact of the faithfulness issue. Here we have a number of blocks that are repeatedly accessed, the scan access pattern. With the increase of the cache size, the misratio curve of LRU does not decrease, and there is a big gap between the curve of LRU and the curve of OPT. And the LIRS addressed this issue with its uniquely defined locality measure. Now let's see how LIRS locality measure helps with its faithfulness. LIRS introduced the concept of reuse distance. It is a time distance between two consecutive accesses of the block. it refers to the most recent one by default. To keep its locality measure up to date, LIRS actually uses the larger of the RU, T-reuse, and the T-last as its locality measure. Instead of estimating OPT's locality measure, the locality measure of LIRS, T-LIRS, is used to define cold and hot blocks. And it's assumed that cold blocks are going to be cold and hot blocks continue to be hot. Now let's see the scan access pattern again, with its locality measure to distinguish cold and hot blocks. LIRS can consistently choose cold blocks for replacement and not be misled by small t-last with recently accessed cold blocks. And we can see that its miss ratio is as good as OPT's. Regarding the steadiness issue, people usually introduce the deeper access history into locality measure to reflect a block's longer-term access behavior. The LRU-2 algorithm is such an example. It uses the distance from the second to the last access to the current time, which is t-last equal to t-reuse and t-last as its locality measure. And the t-reuse is more stable than t-last. And this t-last2 is actually take a longer and thus more stable history into account, right? So it's supposed to be more stable. However, because this t-last2 is a sum of these two locality measures, so the impact of t-last on t-last2's variability is still significant. Another major issue with LRU2 is it is much more expensive than LRU. It is not a big O1 algorithm. LIRS locality measure is more stable than LRU's. However, LIRS may also have its steadiness issue. LIRS mostly use reuse distance T-reuse to determine if a block is either hot or cold, and it's assumed consistency of T-reuse to make the prediction. It's assumed that a small T-reuse is going to be followed by another small T-reuse. A significantly varying T-reuse can compromise its performance. However, we do see in some workloads, T-reuse may change substantially. Let's take a look at this zigzag access pattern. In this access pattern, an ordered list of blocks are repeatedly accessed in alternate directions. Every small reuse distance is followed by a large reuse distance, which is again followed by a small reuse distance. This basically is against the assumption of LIRS. And accordingly, we see this miss ratio is actually much worse than OPT. To address the issue, we naturally come up with the idea of using the sum of two consecutive reuse distances as a locality measure, which helps cancel momentary variations of individual ones. So this T2 reuse, which is the sum of T reuse 1 and T reuse 2, the two most recent reuse distance, it is assumed that there is a consistency between these locality measures, and this T2 reuse is going to be used to separate blocks into hot and cold status. And we propose the LIRS2 algorithms. This LIRS2 algorithm locality measure is actually defined as the larger one of T2 reuse and T-last2 to responsively track recent access events, similarly like what is done for LRU. Now the change is how to efficiently incorporate the new locality measure in a replacement algorithm. We know that the time complexity of LRU is big O1. After adopting a more complicated locality measure, which is T-reuse plus T-last in LRU2, its time cost become big O log n. N is the number of blocks in a cache. And now we have a more complicated locality measure for LIRS2. Can we still make the LIRS2 as efficient as LRU with its big O1 time cost. To understand LIRS2, let's first compare the design principles of LRU and LIRS2. LRU use an always trust strategy. In LRU, every block is trusted as a potentially hot one, and the block is then cached until not accessed for a long time. So in this way, even a cold block may stay in the cache for a long time before it is replaced. And the LIRS2 is different. LIRS2 uses a check and trust strategy. A block is checked on its access to decide its hot and cold status according to its T to reuse locality measure. And only blocks trusted to be hot are cached, and cold blocks will be admitted into the cache but will be replaced quickly. Now let me use an example to illustrate operations in LIRS2. We use an LRU stack to track up to two most recent accesses of a block, named instance 1 and instance 2. Assume there is a block access sequence where block B is accessed multiple times. After first access of block B, B1, the first instance of block B, is pushed into the stack. After second access of B, a new instance 1 is pushed into the stack, and the original instance 1 becomes instance 2. And in this way, we can efficiently track the first reuse distance and second reuse distance of this block. And we assume initially all blocks are hot blocks. Let's continue with this example. In LIRS2, all hot blocks are resident in the cache, and only a small number of recently accessed cold blocks are in the cache, and they're going to be replaced quickly. And the lowest instance 2 of a hot block is always sit at the bottom of the stack to serve as a benchmark. A block whose instance 2 is in the stack when it is accessed becomes a hot block because its locality measure is smaller than that of the max block. If the block is not accessed for some time, its B2 is out of the stack. It becomes a cold block and be replaced. And if this block is accessed again and it's become resident again, but it's still a cold block because at the time it is accessed, its B2 is not in the stack. After some time, this block is replaced because it is a cold block. And if this block accessed again, this block becomes a hot block. And the reason is at the time it is accessed, its B2 is smaller than it's in the stack. So it actually produces a smaller locality measure and be promoted. In the evaluation, we use a diverse set of real-world traces. This includes 106 virtual disk traces from Cloud Physics, 4 traces from Microsoft Research, 5 I/O traces from UMass Trace repository. We choose result of 2 traces to present here. In one trace, LIRS2 perform much better than LIRS and other online algorithms in this ratio. To see the reason, we also plot CDF curves of variations of reuse distance and 2 reuse distance. And we can see that this 2 reuse distance has much smaller variation than 1 reuse distance, indicating that LIRS2 use a more stable locality measure. In the second trace, LIRS2 perform only a slightly better than LIRS. This is consistent to the observation on the locality measure variation distribution curves. While T reuse already have small variations, there is little room for LIRS2 to improve. Here are some takeaway messages. General purpose replacement algorithms still have room for further improvement. If we choose to use a more history-rich locality measure, the efficiency of the algorithm should not be compromised. The LIRS2 give an example of such effort.
Okay, so that was great talk. So we have Chen here who's going to answer questions. Yeah, as always, please post them on Slack or raise raise your hands on Zoom. So while we wait, I had a couple of questions. So let me get started with that. So I really like the idea of having, you know, the most recent reuse distance plus the penultimate reuse distance and adding them together. So I was wondering, why stop at two? And did you explore going back further in an object's access history? And you know, would, let's say, LIRS3 be any different than LIRS2?
Oh, that yeah, I think that this is kind of a trade-off. If we use two reuse distance and even three or four reuse distance, the the time overhead will be increased. So I think except we use one reuse distance, two is more better, I think.
Okay.
And there are also another research like LRU2, and they also used it's kind of like look two times before current access. Yeah.
Right. Yeah, it makes perfect analogy. So the other thing, just to expand on what you touched upon, the sort of computational overhead of keeping these extra reuse distances and computing the eviction priorities. Uh, how much is that computing overhead compared to something very simple like LRU?
Oh, for LIRS2, with only a few instructions for updating pointers and the block status upon an access, they are efficient as LRU because for LIRS2, every block access up to three operations, that is the same as LRU. Like when a new block access, we put the block to the top of the stack, and maybe there will be a second operations like, and we remove the instance 2 from the stack. Yeah.
Okay.
It's almost the same as the LRU. So we confirm that it is the O1 time complexity.
Nice. Yeah, great. It seems extremely versatile and general, and look forward to using it.